Well, thank you. Uh, the title of the presentation, FAST, was supposed to be about the technique, curious about the geologists who use them. Seeing that we're kind of late, I'll be fast, and hopefully you'll be curious enough to ask me questions later. Just who we are, IOS. So the company was founded in 1992 by 5 grad students without a job. One kept going, became the sole owner, and with the time we developed a really good know-how in indicator mineral, especially during the diamond rush in the early 2000s. And push come to shove, we migrated to automated mineralogy in the mid-2010s. And now we use indicator mineral, but our lab is used by clients all over the world, industry, universities, government. We own 2 SEMs. As far as I know, we're the only commercial lab with 2 detectors on one, and we added the EBSD, which I'll talk a bit later, to one of the SEM as well. So I'll skip that one. So what is commonly used for indicator mineral studies? Usually it's limited to coarse grain, because if you go into the really fine grain, it's really hard to work with. Use a microscope, so there's so much you can do with it. It's often limited to a few key minerals, so if you find some oddities, you often don't know what it is. And it's really time consuming. And I mean, for young geologists starting with that, they get bored really quickly, and you have to retrain new people, so it's not the best thing. Other technique, MLA and QuEM-scan before that. They are limited to libraries, so it means that they can identify mineral, but only if it's in the software. So if you find odd minerals, they won't know about them. Sometimes it can be project limited, or if you're lucky enough, you have a really wide library, so you can have some oddities in them, but it's not the best. It provides generic chemical data, so if it identifies, say, a hornblende, it will give you that end member of the hornblende family. You won't be able to see like little variation in chemistry that could be useful to you. I'm too short, I don't see the screen in front of me. But MLA can be useful for geometallurgy in a known environment, so you know what to expect. So it could be useful in those circumstances. At the other end, you can use ICP-MS. So it's really good for the trace element chemistry. There's a lot of paper using trace element in tourmaline, garnets, magnetite. It's really useful if you're working with the host rock. So if you have a granite, you analyze the magnetite within the granite, and it can tell you if it's a good granite for porphyry or whatever. But when you work with till, with detrital, it could be stream sediments, you don't know where it comes from. So you don't want to spend money analyzing all the magnetite grain in your sample. It will cost way too much. And it's slow. So we decided to use the SEM, scanning electron microscope, to do the mineralogy of the heavy mineral concentrate. So one product we use is what we call ARTMIN for minerals. Art, there's several definitions depending on how you feel, so you can make up your own, doesn't really matter. So it was developed with speed in mind, as many samples as possible in a short time. It's based on energy dispersive spectrometry, if I'm not mistaken. I'm not the technical guy, so and the time used for every sample depends on the count, the process time, the resolution you want. But it's independent on the number of grain that you have in your sample. So it's fast. You can work the number like you want, but we were able to count and, more importantly, identify about 600,000 grains a day. and it's not limited by library, and I'll show you why. The nice thing, each of the grain is georeference on the mount, so you can take that grain and reassay it or take it to the ICP-MS for more detailed trace chemistry. So you can take that from one machine to another to get more detail. So the way it works, it scans, it's like a little puck. So you get the chemistry of each pixel. And from that, so that's where you see there. So you have like the general map to the left, and then you have the, is it potassium? No, it's carbon, titanium, iron. Anyway, you get a map for each element for each pixel, and then you put that in the software, and based on the chemistry, it will tell you which mineral it is using AI software that we developed in-house. So not the other way around, not telling you, oh yeah, that's ilmenite, and it should be this chemistry. So we have the chemistry, and it tells you, well, it's ilmenite, but there's a little bit of manganese in it. So that's why it's really interesting, because you get more detail in what you have. So an example, I mean, there's obvious project. If you work with diamond, you look for diamond chrome dioxide. That's fairly easy. If you're working in gold, well, you'll look for gold. But look at some kind of more difficult project using that type of approach. So if you look for lithium, well, the thing is, lithium is not measured by the SEM. It's too light. So how do you identify lithium mineral if you don't have lithium? What we did is we just basically took a bunch of several lithium minerals, put them in the SEM, and worked with the aluminum to silica ratio. And it works really, really well. So we were able to identify all the lithium mineral except for spodumene, because it has the similar aluminum to silicium ratio than pyrophyllite. Sorry, I'm really bad at mineral names in English. So basically, obviously, it means that there's no iron, there's no nothing else. For spodumene, you would have lithium, aluminum, silica. There's no lithium, so you only have Al and Si. And pyrophyllite, that's all you have. I talked before, we added an EBSD, which is the electron backscatter diffractometer. So basically, you have the crystalline structure of the mineral you have. So if you end up with one or the other, spodumene or pyrophyllite, then you open DBSD and tells you there's no confusion between the two, so you can confirm that, yeah, it's a lithium mineral. Porphyry is another interesting system, because in that gold is usually fine-grained, which is it's really difficult to see even with a binocular. There's no real distinctive minerals. In that case, what we do is we use trace mineral for the alteration zone. And even then, they're either a light mineral or they come in really in trace. So instead of using one mineral, we use some assemblage. So I won't go through all the detail, but we ended up, that's a sample from the Andes. All bunch of APS, aluminum phosphate sulfate, aluminophosphate sulfate, bunch of weird mineral from alteration. And we were able to come up with, okay, these are from the oxidation of sulfide. The other ones are primary sulfate. Then you have oxidation of sulfide as well, but another type. And then you have the alteration of phosphate due to presence of sulfide. So you can use those, and they are in trace. I mean, probably attached to heavier mineral, and we pick them by accident, but since we identify anything, we have them. And like beaverite, it's a copper, lead, APS. It was probably at 0.1% in the sample, but it's there and it's significant. So we just don't rely on what's coming out of the SEM. We make sure that we it makes sense. So we calculate the stoichiometry for, sorry, for all the mineral that comes out. It enables us to confirm the nature of the less common mineral, and also to see if there's something odd with more common mineral. Like I said, if you have ilmenite, then you can pick up traces of manganese or zinc in it. So it could be, it increase our and your knowledge, and you can interpret the data with more confidence. So that's just an example of what we do. We put everything in graph just to make sure it makes sense. The problem with Artmin, it's we learn too much or we don't know enough. So we pick up all kinds of things. For example, in almost every sample from Quebec, we pick minerals from the pyrophanite eckentrusite series, which are manganese, zinc, ilmenites. What does that mean? We don't know. Is it significant? We don't know. Same thing for the spinels. So there's so many data, and sometimes when you look on the internet, oh yeah, this mineral is from that location somewhere in Africa. So how come I have it in Quebec or in Labrador? So what does it really mean? So we have to work on this. And obviously, people who provide the sample have something to have fun with. Art gold, like the name says, is more. It was developed for gold because it uses heavier minerals. So with time, it came to be really useful for PGM, so platinum group mineral, and every very dense mineral like tantalite. So basically, what we do is the sample, the 10 kilogram sample, are processed. We end up with about 100 milligrams of really dense samples. We put that in the SEM, and with the density, with the backscatter image, we eliminate everything that's below 5.5. Why 5.5? It's a monazite density, and there's so much monazite in every sample that you don't want to bother to analyze that. So we only analyze the really heavy dense mineral. So once we do that, the first thing is obviously count the grain. We have a really, really good recovery. If you work with gold, our system will probably have close to 100% recovery in 20 micrometers and above. And as the grain gets finer, we lose them a bit, but it's still way better than the usual Wilfley table and counting with a binocular. So why is it important to recover a lot, and especially why is it important to recover and identify small grain? That's the grain size of gold in till from all Canada and some region. So when you use a binocular, 50 micrometer is as much as far as you can go on grain size. Below that, some people say, oh yeah, we can go down as 20 micrometers. I really, really doubt that because it's way too fine. But the thing is, if you cut at 50 micrometers, you lose about 70% of the gold because naturally the gold is not coarser. There's only 25% of natural gold that is coarser than 50 microns. So you lose all of that. So depending, if you work in orogenic gold, there's about 20% of the gold that will be recovered. If you work in VMS, that's about 10%. And if you work in a porphyry system, just by sieving or on the Wilfley table, you lose all the gold if you take only 50 microns and up. The second stage for art gold is using the chemistry. So you eliminate all false positive because you actually measure if it's gold or not. You have the chemistry, and you can identify other elements that are in the alloy. So here, that's an example from Borden in Ontario. So the background gold had a certain silver signature, and gold from the deposit, the actual deposit, had another signature. So you can tell if your gold is from the deposit or not. So it's helpful if you have a high count or just a few grain, you can say, oh yeah, those few grains are linked to mineralization or not. And then there's the shape, something that's been used for a while. With the SEM, we take picture of all the grain. There's an algorithm that can classify the shape. Those shapes there are subclasses of the pristine category that's been used in the literature. So we go a bit further, and everything is automated. We have a geologist that look afterward if it makes sense, but it's all from parameter measured with the SEM. Our gold, like I mentioned, it's gold, PGM, other minerals. In case of lithium, it's really useful because you can identify the tantalite for the tantalum in LCT pegmatite. And not only you have a count of tantalite, you know the tantalum to niobium ratio, which is really important because if you have more tantalum, you're looking at LCT. If you have more niobium, you're looking at NYF pegmatite, which is totally, well, not totally different, but you won't find any spodumene in NYF. So it's really, really important. And then you have tin and manganese as well in there, so you can tell if you're in a really good setting or just a okay setting. So use the SEM. If you combine that with years of experience in in-house development, so for us, it took about 10 to 15 years to get where we are right now. It's fast. It's not limited to libraries. So there's a wealth of information. Like I said, some information we still don't know what it really means. So there's a lot of thinking geologists can have fun with. So it can be done. I showed example for indicator minerals from till, but we use it on thin sections as well. The talk was more like exploration oriented, but it can be used for geometallurgy. So if you want to calculate the liberation and dolmen deportment, we do that. It can be done as well. More and more in the environment, so looking at the tailing, so looking at the dust, more and more like engineering firms, we have people coming in for that. And I think that's it. So if you have any question, if you are curious, I will be hanging around for the next 2 days. And my colleague Jonathan is here as well. He's more technical guy. So yeah, just we can have a beer and chat about it. Thank you.